Hi, my name is Anton Grigoriev. I'm a lead developer in the Gamma DNA company. I'll show you the program recovering the oligonucleotide sequence. The program is designed to recover the nucleotide sequence of the sequence DNA fragment on the basis of the attachment of free nucleotides during the polymerization reaction of the DNA's fragment time delays data. Let's start with the input data. The input file is in YAML format. The program can also work with JSON format. The input file contains the nucleotide sequence with the primer we use and a set of time sequences cyclograms. Here are 4 cyclograms that were obtained from the results of the oligonucleotide polymerization in 4 solutions with the different types of reduced nucleotide. The reduced nucleotide parameter indicates the type of the nucleotide which concentration was reduced in this solution. The delays parameter contains the time delays array. This is the time that the polymerase spent to attach next nucleotide in the chain of the polymerized oligonucleotide. The data for this input file was obtained by modeling. My colleagues are at the final stage of obtaining the real data. Soon, we will be able to demonstrate another video using the real data to recover the nucleotide sequence of the oligonucleotide. Now, let's move on to the program. We are opening the source file with the program. Right after loading, the oligonucleotide is recovering. The recovery has already ended, and it's ended successfully. Here at the bottom of the window, you can see that all 177 nucleotides out of 177 were recovered. That is 100% accuracy. It took the program slightly more than a second. We can also demonstrate the same accuracy on the real data. The information here shows the stages of our original algorithm. The first table shows the source data statistics. You can see how many delays for each solution were obtained, as well as the minimum, maximum, and arithmetic mean values of these delays. The next step is data normalization. At this stage, the source data is aggregated to the size of the oligonucleotide, which is 177 samples. As you can see, on average, it's about 2 complete polymerization cycles. The next step is finding the threshold. We needed to differentiate long delays from the short ones. To do this, we begin to iterate the threshold value in ascending order, starting from 2. Here, we determine the nucleotides in accordance with the threshold value and try to find the best entry of the primer in the resulting sequence. It can be seen that the best result is shown when the threshold values are from 10 to 44 inclusive. When the threshold value is 45, we see descent. The search stops here because next samples will show only a recession. And the final stage. For the thresholds from 10 to 44, we have recovered the oligonucleotide completely. And we can see how many nucleotides here determined for each threshold value. As you see, delays from 10 to 21 allow us to recover the sequence completely. I would like to draw your attention to the time spent by the program once again. In current case it may seem little, but in the future we plan to make post-processing of the whole matrix, and this will be about 5 million independent calculations. It should be noted that now the program spends most of the time searching for the optimal threshold value. While processing the matrix, we will perform this search only once, and this will significantly reduce the time which the program spends on the whole matrix. Let's move on to visualization. The delay distribution chart shows the delay values on a logarithmic scale by the oligonucleotide positions. After pressing the stop button, the program processes first 5 delays from each solution. It can be seen that the polymerization starts in random places. This creates certain difficulties for calculations, but we successfully cope with them at the stage of searching the primer position. As the program processes the subsequent data, we can recover the oligonucleotide. The program is running until it's fully recovered. During this demonstration, the program makes 2 steps per second. For each step, 5 nucleotides from each solution are calculated. Therefore, the complete recovery of the oligonucleotide will take some time. Let's wait for the end. As you can see, it took 335 delays for the full recovery, and this is slightly less than 2 polymerization cycles. Thus, we can achieve the required accuracy of 100% at the planned sequencing time. Thanks for your attention.